So I showed you guys in class how to balance chemical equations, both with what a lot of people like to call the guess and check method, and then I showed you guys with algebra. And I have videos with the guess and check method, but I don't have any videos with algebra. So I'm going to go ahead and show you guys a few examples right now. Let's start with this same worksheet that we're going to go over, I'm going to post answers and stuff to later that you're going to use to practice. And we're just going to start with problem number 1. Okay, so I'm going to rewrite this here bigger so you can see it. So here we're forming water from hydrogen and oxygen. Okay, and I can go ahead and point out a couple things just for some extra review. I see that oxygen, O2, by itself as an element is a reactant in this chemical reaction, or in this equation. I can see that a little easy. Here you go. There you go. Let's get that up so you can see it. So I know that this has to be combustion, okay, because of the oxygen as a reactant. Also, this is a synthesis reaction because only one product is formed. So we can classify that before I do anything else to it. Okay, I see O2, that's combustion. I see one product, that's synthesis. Okay, all right. As far as balancing this the algebra way, I'm going to assign some numbers. It's got a different colored pen. All right. We're going to call this reactant species A. This will be reactant species B, and this being our only product, we're just going to go ahead and call that just species C. So we've got A, B, and C. And you think about A as being hydrogen gas, and B is oxygen gas, and C is water. The cool thing about the algebra method is that it does really do a good job showing that law of conservation of mass in action. If we want to think about a molecule of H2, I know it's going to have 2 atoms of hydrogen bound together to be 1 unit of A, or 1 molecule of hydrogen. Okay, so I've got 1 chunk of A, but there's 2 hydrogen atoms there, so we can see that there's 2 H's for every 1 A, which is this chunk, okay, or that 1 molecule. If I look at species B, now it's still just 1 chunk of B, but it's got 2 oxygen atoms. I'll make oxygen filled in. Okay, so we've got 2 individual atoms bound together to make 1 unit of B. So there's 2 O's for every B. Okay. If I look at C over here, I have 2 hydrogens and 1 oxygen all bound together. All right. As 1 unit, so there's 2 hydrogens and 1 oxygen for every 1 unit of C. And this is going to be helpful when we move down here to start working out the problems. Okay, this method works if you go ahead and kind of make a little list off to the left side of your elements. Okay, so we've got hydrogen and we've got oxygen. And what we need, the law of conservation of mass says, however many atoms of hydrogen I have on my left side or in my reactants, I must have the exact same number in my products or on my right side. So I need not only the total number of atoms to be the same, but the atoms of each kind to be the same. And we've discussed that a chemical reaction really is just making bonds and breaking bonds and breaking bonds and making bonds, and all it's doing is rearranging the atoms that are there. Okay. So if I look at so basically you can say law of conservation of mass says that my reactants must equal my products. So I'm going to use an algebraic formula to express the number of atoms of each kind in reactants and say that that must be equal to the same proportion in products. So if I look at my reactant side for hydrogen, I see that if I have 1 unit of A, I've got 2 hydrogens. So hydrogen is going to be 2 times whatever A is. Okay, so if I've got A, so that means I've got 1 unit of it, I've got 2 hydrogen atoms. If I have 2 units of A, I've got a total of 4 hydrogen atoms. So I've got 2 times however many A's I've got. That's my reactant side, so that has to equal whatever I have in my products. Okay, every C that I have, I've got twice the number of hydrogen, so hydrogen is equal to 2 times C, or the number of hydrogen atoms would be 2 times however many water molecules I have. Okay. Let's do the same thing for oxygen. I see that for every B, I have twice the number of O's, or oxygen atoms. So oxygen atoms are going to be 2 times whatever B is. So I've got 2B for my reactant side. And then if I look over my product side at oxygen, for every C, I've only got 1 O. So however many however many water molecules I have the same number of oxygen atoms. So in that case, I've got C. If you write down your variables, A, B, and C, and pick one of them to be 1. Now, just to keep things simple for us, let's just always make A equals 1 so you're not having to guess which one would be best. It works no matter which one you pick. So I'm going to just always make A equal to 1. That should be a good way to solve these problems every single time. Okay. What you do at that point is you go through and try to figure out, well, how many A's to B's to C's do I need? So if I need 1A, that means that I've got 2 times 1 is 2 times C. So 2 is equal to 2C, which means that C is just 1. Okay, well, when I see 2A is 2C, A must equal C. Okay, I can use C to find B. So I need 2 times the number of B's to equal whatever my number of C is. Or I can write that 2 times B is equal to 1. Divide both sides by 2. And I get B is equal to 1/2. Okay, which means that I need 1A, half of a B, and that's going to make me 1C. Or if I look at A, I've got 2 hydrogen atoms. If I have half of that, that's 1 oxygen atom, and if I put those together, I'm going to form 1 water molecule. However, I can't just split that oxygen atom in half and leave the oxygen molecule, in half and leave just an oxygen atom hanging out. So again, we can't have any half numbers or incomplete numbers here. So what we're going to do is we're going to see, well, to get rid of a half, I've got to multiply everything by 2, or multiply this by 2 at least, and if I multiply everything by 2, it's going to keep the same ratio. So 1 times 2, that means I've got 2 H2 molecules. Those 2's cancel, that gives me 1 and 2. So now I need 2 hydrogen molecules to react with 1 oxygen molecule to give me 2 water molecules. So I'm going to have 2, understood 1, and 2. And those should be my coefficients to balance my equation. Okay. All right, now I'm not going to spend as much time on the next couple examples explaining the process. Instead, I'm just going to work the problem so that way I'm not spending a whole bunch of time repeating myself. Okay, this works all the time. So I'm not going to work my way down the list and work every single problem. Instead, I'm going to try to increase in difficulty. So let's try this example here. So now we've got zinc plus hydrochloric acid, which we did this reaction in class. This is a single replacement, and I'll show you guys why. All right, those are going to react to produce zinc 2 chloride and hydrogen gas. Okay. All right, now in this example, we know that this is a single replacement because I've got an element and a compound, and I can see on my reactant side that this element replaces this element in the compound. So instead of H and Cl, now I've got zinc and Cl. All right, and now the H is, all by itself. So this guy was replaced. The only one thing was replaced. This is single replacement. Okay, I remember this. I got an element and a compound, making a different compound with a different element. They kick each other out or swap spots. Okay. All right, as far as balancing this goes, let's go ahead and we're going to say this is A, B, C, and D. All right, if I look at my elements, I've got zinc, I've got hydrogen, and I've got chlorine. All right, however many A's I have, I've got the same number of zinc atoms. So I'm going to say that I've got that same number of A for my reactants has to equal the number of zinc atoms in my products. For every C, I've got just 1 zinc. So for every zinc 2 chloride, I've got 1 atom of zinc. So I can say that. Okay. If I look at hydrogen here, I've got 1 unit of B, so 1 HCl should give me 1 H. So whatever B is, that's how many hydrogen atoms I have. And that equals 2 times D, right? So every D, I've got 2 atoms of hydrogen, so The number of atoms is 2 times whatever D is. Okay. For chlorine, I've got just B in my reactant side, and that's going to be equal to 2 times whatever C is. Got A, B, and C. And let's go ahead and set A equal to 1. Well, if A is 1, then C is 1. Oops, I always do this. Okay. Well, I don't know B or D, so I'm going to skip that one. I'm going to move on. Here I've got 2 times C is equal to B. So B is 2 times 1. So B is 2. Okay. So now I can use this one and say 2 is equal to 2 times D. So D is equal to 1. So that means I need 1 zinc atom for 2 hydrochloric acid molecules to give me 1 formula unit of zinc 2 chloride and 1 molecule of hydrogen gas. So we've got a 1, 2, 1, 1. But look here, now I've got 1 zinc, 2 hydrogens, 2 hydrogens, 2 chlorines, and 2 chlorines. Now, for me, I feel like this method takes a long time for a problem this simple, but it's one of those things that if this is your preferred method, it works every single time. So it's worth spending the extra time to do it if you're still struggling balancing, the other way at least. Okay, let's step it up a notch. Let's work this problem here. So I've got SiCl4 plus H2O yields H4SiO4 and HCl. Okay. Let's go ahead and go through and name these, A, B, C, and D. Okay. All right, my elements, I've got silicon, I've got chlorine, I've got hydrogen, and I've got oxygen. Okay. For silicon, I've got just whatever A is, and that's my reactant side, has to equal my product side. I've got 1 silicon for every C, so C. Chlorine, I've got 4 times A. I'm keeping capital letters here. And that should equal just D. For hydrogen, I've got 2 times B. And this is where it gets kind of funky for people. Here I've got 4 hydrogens for every C, plus 1 oxygen for every D. So I'm going to say 4C plus D. So 4 times whatever C is plus whatever D is. Okay, and then for oxygen I've got B is equal to 4 times C. Okay, all right. Let's go ahead and write out A, B, C, and D. And let's set A equal to 1. Well, if A is 1, then C is 1. Okay, 4 times 1, so 4 times 1 is D, so D is 4. Okay, I can find B a couple ways. I see that that's going to require more plugging and chugging, so let's just, do this. All right, so B is going to be 4 times 1 for C, so that's also 4. Let's say that you chose to use this equation instead. You should get the exact same thing. Let's take this off to the side. So now I've got 2 times B is equal to 4 times 1 plus 4. So 2B is equal to 4 plus 4. So 2B is equal to 8. Well, it's still 4. Okay. Either way. So that means I need 1 of these for every 4 water molecules. Okay, that's going to give me 1 and 4 HCl. Okay, you can just triple check if you need to. Got 1 silicon, got 4 chlorines and 4 chlorines, 8 total hydrogens, and I've got 4 plus 4, so that's 8, and a total of 4 oxygens, just like I do here. And so it's balanced. I'm going to show you one more example. So you've seen what happens if you have an element that appears in more than one place on either the reactants or product side. I just want to do one refresher on the way that parentheses work. Okay. So if we look at, say, let's pick one with a lot of parentheses. Let's see if we got one with a bunch. No. Let's do this one. So I've got carbon dioxide. I'm a little bit dyslexic when I write. Okay. Again, I can name these A, B, C, and D. My elements present are carbon, oxygen, nitrogen, and hydrogen. Okay, I see that I've got carbon should be the same number of A, and that should also be the same number of C over here. So 1 carbon for every CO2, 1 carbon for every OCNH22. Oxygen, I've got 2 times whatever A is. 2 oxygens for every one of the CO2s. Okay, and that must equal C plus D. Okay, well, since I can already see that if A is C and 2A is C plus D, then D must be whatever A and C are, but just triple check. Okay, nitrogen I got B is equal to 2, so the distributive property works this way. I've got 2 times nitrogen here, so 2C. Okay, and for hydrogen I've got 3B is equal to this distributive property that also goes to the hydrogen. So I've got 2 hydrogens times 2, that's going to be 4 hydrogens. But remember, I've got plus 2 over here for water. Okay, got A, B, C, and D. Let's make A equal to 1. Let's do that in blue. So A is 1. Well, that means C is 1. So 2 times 1 should be C plus D, right? Or 1 plus D, so D should also be 1. B should be 2 times C, which is 1. So B should be 2. Okay. I could have done it this way too. All right, I can see that 3 times... I'm going to go ahead and just plug in what we have because, you know, if you would have used this to find, you know, B, C, or D, given what you know from a previous 1 or 2 formulas, you should be fine. So I'm just going to just show you that the numbers we found through these work the same in this problem here. So I've got 3 times B is 2 is equal to 4 times 1 plus 2 times 1. So 6 is equal to 4 plus 2, which is 6. Well, that's exactly true. So I could have known B and D and found C, or vice versa, or whatever. Okay, so that means I need 1, 2, 1, and 1. I can triple check. I've got 1 carbon and only 1 carbon. I've got 2 oxygens and I've got 1 oxygen, 2 oxygens, and there you go. Yeah, I had that right there. Okay, I've got 2 nitrogens and I've got 2 nitrogens, and I've got a total of 6 hydrogens here. 2 times 3 is 6, so I've got 4 here plus the 2 there. So we're balanced. Hope this helps.